You flip a switch and the room lights up instantly. No delay, no waiting, no sense that anything had to travel any distance at all. It just happens. And because it feels so immediate, your brain fills in a story you have probably believed your entire life. Electricity flows through the wire. Tiny electrons leave the power plant, rush through miles of copper, pass through your walls, enter the bulb, and make it glow. It sounds reasonable. It sounds physical. It sounds like water moving through a pipe. But there is a problem with that picture, a serious one, because if that story were actually true, your light should not turn on instantly, not even close. Think about it carefully. The electrons inside a wire do move, but they do not move the way you imagine. They do not shoot forward at high speed like bullets. They drift slowly, painfully slowly. In fact, in a typical household wire, an electron moves at a speed measured in millimeters second millimime. That is slower than a snail, slower than the growth of your fingernails. If an electron had to travel all the way from a power station to your house, you would be sitting in the dark for hours before anything happened, maybe longer. And yet, that is not what you experience. You flip the switch, and the light responds immediately as if something moved at nearly the speed of light. So now you are stuck with a contradiction. On one hand, you've been told that electric current is the flow of electrons. On the other hand, those electrons are barely moving at all, and yet somehow the effect arrives instantly. Something is clearly happening, but it is not what you think. And once you see what is really going on, you will realize that the way you have imagined electricity your entire life is not just simplified. It is fundamentally misleading. Now let's slow this down and really look at what is supposed to be happening inside that wire, because this is where everything starts to fall apart. You were told that electric current is the movement of electrons. That is the definition, charge and motion, and technically that is true. But the moment you try to imagine what that actually looks like in reality, you run into a problem that most people never notice. Picture a copper wire. Inside it, there are trillions upon trillions of electrons, already there before you ever touch a switch. They are not waiting somewhere far away. They are already inside the metal, packed together like a dense crowd. When you flip the switch, you are not releasing a stream of new electrons from a distant source. You are disturbing the ones that are already there. Now here is the key detail that breaks the entire intuitive model. These electrons do not suddenly take off at high speed. They do not race from one end of the wire to the other. What they actually do is incredibly underwhelming. They drift slowly with constant collisions, bouncing into atoms, losing direction, barely making progress forward. If you could zoom in and watch them, it would look chaotic. Not a smooth flow, not a clean stream, more like a crowded room where everyone is trying to move forward, but keeps bumping into each other every fraction of a second. The average motion forward is tiny, almost negligible. And yet, despite that slow, messy motion, something about the system reacts instantly when you flip the switch. The bulb does not wait for individual electrons to arrive. It responds immediately. So ask yourself a very precise question. If the electrons themselves are barely moving, then what exactly is moving through the wire so fast that it makes your light turn on instantly? Because whatever the answer is, it cannot be the simple picture you were given. And that means the most basic idea you have about electricity is not just simplified. It is hiding something much deeper. At this point, most people try to resolve the contradiction in the simplest way possible. They say, maybe the electrons actually move faster than we thought, or maybe the ones near the switch are different from the ones near the bulb. But none of those explanations survive careful thinking, because the real issue is not speed. The issue is how we are even defining current in the first place. You were taught that electric current is the flow of charge, and that definition is correct. If charges move, we call that a current. But notice something subtle. That definition does not actually say anything about how fast individual electrons have to travel from one place to another. It does not say anything about distance. It only says that charge is moving locally. This is where the misunderstanding begins. Because when most people hear the phrase flow of electrons, they imagine something very specific. They imagine particles leaving one place and arriving somewhere else, like water going from a tank through a pipe to a faucet, a journey, a path, a start, and an end. But that mental image is doing a lot of hidden work. It is adding assumptions that are not part of the definition at all. The definition never said electrons had to travel across the entire wire. It never said the same electron that leaves the power source is the one that lights up your bulb. That is something your intuition added because it feels natural. In reality, something much stranger is happening. The electrons inside the wire form a continuous system, a chain that already exists everywhere along the circuit. When you flip the switch, you are not sending something from point A to point B, you are disturbing the entire system at once. And this is where things start to get uncomfortable, because now the idea of flow begins to break down. If every electron only moves a tiny amount, but the effect appears instantly at the other end, then what you are really seeing is not a journey of particles. It is a transmission of something else, something that spreads through the system much faster than any individual electron ever could. So the textbook statement is not wrong. Current is the movement of charge. But the picture in your head of electrons racing through wires like cars on a highway is not what is actually happening. It is a shortcut, a simplification. And like many simplifications, it works just well enough to hide the deeper truth. So what are the electrons actually doing inside the wire? If you could somehow shrink yourself down and watch what happens at the microscopic level, you would not see a clean stream of particles moving in one direction. You would see something messy, chaotic, almost random. Each electron is constantly colliding with atoms in the metal lattice. Every fraction of a second it gets knocked off course. It jitters, it vibrates, it moves a little forward, then gets pushed sideways, then backward, then forward again. The motion is not smooth. It is not fast. It is more like a drunk crowd trying to move through a packed room than a group of runners sprinting down a track. And yet there is a tiny bias in that chaos, a slight push in one direction. Over time, that bias creates what we call drift. The electrons, on average, move forward. But that forward motion is incredibly slow, almost insignificant, compared to how fast the effect of electricity seems to travel. This is where your intuition completely breaks, because everything in your experience tells you that if something moves slowly, then the result should also be slow. If a drop of water moves slowly through a pipe, then the water at the other end takes time to arrive. That is how cause and effect usually works. But electricity refuses to behave that way. The individual particles are slow, but the effect is fast. So the thing you are seeing cannot be explained by tracking the journey of a single electron. That is the wrong level of description. Instead, think of it like this. Imagine a long line of people standing shoulder to shoulder. If the person at one end leans forward and bumps the next person, that motion is passed along the line almost instantly. Each person only moves a tiny amount. No one runs from one end to the other, but the effect travels through the entire chain very quickly. That is much closer to what is happening inside a wire. Each electron nudges the next. Each interaction passes something along, not the electron itself, but a disturbance, a change, a signal that propagates through the entire system. And once you start to see it this way, the original picture of electrons flowing like water begins to fall apart completely. Because what matters is not how far any single electron travels. What matters is how quickly that disturbance moves through the network of charges that are already there. Now take that idea one step further, because the line of people analogy is not just a helpful image, it is dangerously close to the truth. Imagine again that long line stretching from the power source all the way to your light bulb. Every person is already standing in place. No one needs to run across the room. No one needs to travel the full distance. When the first person moves even slightly, that motion is passed along immediately. One pushes the next pushes the next, and so on. What matters is not how far each person moves, it is how quickly the change traveled through the This is exactly what happens inside a wire. The electrons are already everywhere. along the circuit. When you flip the switch, you do not send a group of electrons on a journey. You create a disturbance, and that disturbance propagates through the entire system almost instantly. That is why the light turns on right away. Not because electrons raced from the power plant to your bulb, but because the electrons already inside the wire began responding all at once, each one nudging the next, passing along a change that moves far faster than any individual particle ever could. If you prefer a more physical picture, think about a pipe filled completely with water. If you push water into one end, water comes out the other end almost immediately, not because the same molecules travel the entire length in that instant, but because the pressure change moves through the fluid. Each molecule pushes the next. The effect travels quickly, even though each molecule only shifts a tiny amount. Electricity works in a similar way, but even more extreme. The push is not mechanical pressure. It is something more abstract, a kind of influence that tells each electron how to move. And that influence spreads through the system at enormous speed. So when you say current flows through a wire, you are not really describing a stream of particles moving from one place to another. You are describing a chain reaction, a coordinated response of countless charges already in place, all adjusting together as a disturbance sweeps through them. And once you see it this way, a new question appears. If what is really moving is not the electrons themselves, but a disturbance that tells them how to move, then what exactly is that disturbance made of? Because that is the part the simple picture never explains. The answer is something you cannot see, cannot touch, and probably were never told to take seriously. It is the electric field. The moment you flip the switch, an electric field appears throughout the entire circuit, not gradually, not step by step, but spreading outward at a speed, close to the speed of light. This field exists in the space around the wire and inside it. And it is this field that tells every electron how to move. That is the missing piece. The electrons are not deciding to move on their own. They are responding to the field. Each one feels a force that pushes it slightly, creating that tiny drift you learned about. But the important part is not the motion itself. It is how quickly that instruction reaches them, because the field does not crawl through the wire like a particle it propagates. It spreads through space as a change in the electromagnetic environment. And it does this incredibly fast. So when you flip the switch, you are not launching electrons on a journey. You are changing the field everywhere along the circuit. And that change reaches the electrons near your light bulb almost immediately. Those electrons begin to move right away, transferring energy into the filament, producing light. Nothing had to travel from the power plant to your bulb in that instant. The system was already there, fully connected, waiting. All it needed was a signal, and that signal was the field. This is the point where the old picture completely breaks. Because if what actually spreads through the system is a field, not a stream of particles, then saying electricity flows through the wire is at best an approximation. It is a convenient story, but it hides the real mechanism. What truly moves through the circuit is not matter in the way you imagined. It is influence, a pattern in space, a field that carries instructions and energy from one place to another. And once you accept that, the wire itself starts to look very different. It is no longer a pipe carrying electrons from point A to point B. It is part of a larger system where space itself plays an active role in how electricity works. Now, here is where the story takes a turn that almost nobody expects. Because if the electric field is what spreads through the circuit telling electrons how to move, then you might still be holding on to one last assumption. You might still be imagining that the energy itself is traveling inside the wire carried along by those moving charges. That feels reasonable. The wire is where everything is happening. The electrons are inside it. So the energy must be inside it too, but that intuition is wrong. The energy is not flowing through the wire. It is flowing around it. This is the part that even many engineers never stop to visualize. When current flows in a wire, there is not just an electric field. There is also a magnetic field created by the moving charges. And when you combine these two fields, something remarkable happens. They form a pattern that carries energy through space, not through the copper itself, but through the space surrounding it. If you could see it, it would look like energy streaming along the outside of the wire, guided by the fields that wrap around it. The wire is not the pipe carrying the energy. It is more like a structure that shapes the path the energy takes through the surrounding space. This idea is captured in something called the Poynting vector, which describes the direction and flow of electromagnetic energy. And in a simple circuit, that direction points from the power source through the space around the wires and into the device you are powering. So when your light turns on, the energy that lights the filament does not arrive by electrons physically traveling from far away. It arrives through the electromagnetic field surrounding the circuit flowing into the bulb at nearly the speed of light. The electrons inside the wire are still essential. They respond to the field. They interact with the material. They allow the system to work, but they are not the carriers of energy in the way you imagine. They are part of a larger process that is mostly happening in the space around them. And this is the moment where the entire picture flips. The wire is not a tunnel for electricity. It is a guide, a boundary, a way of shaping invisible fields that move through space and deliver energy exactly where it is needed. What you thought was happening inside the wire is actually happening outside of it. And once you see that, it becomes impossible to go back to the old picture. Now go back to the moment you flip the switch, because with this new picture, that simple action becomes something completely different. You are not opening a gate for electrons to start a journey. You are not releasing anything that needs to travel across distance. What you are really doing is creating a change in the electromagnetic field that already fills the entire circuit. The wire, the bulb, the switch, the power source, all of it is already connected as one system. The electrons are already there. The structure is already complete. Nothing is missing. So when the switch closes, the system does not need time to send electricity somewhere. Instead, the field rearranges itself almost instantly. That change spreads through the circuit at a speed close to light, reaching every part of the system nearly at the same time. And the moment that change reaches the filament in your bulb, the electrons there begin to move. Not because new electrons arrived, but because the ones already inside the filament are now being pushed by the field. They start colliding with atoms, transferring energy, heating the material until it glows. That is why the light turns on immediately, not because something traveled fast through the wire, but because the entire system responded as a whole. This is a completely different way of thinking about cause and effect. You're used to the idea that something has to move from one place to another to produce a result. It is a change in a field that exists everywhere in the system at once. And once you see this, a lot of everyday experiences start to look strange. Every time you charge your phone, every time a circuit responds instantly, every time electricity seems to act without delay, what you are really seeing is not particles rushing through wires. You are seeing the behavior of fields reorganizing in space. The wire is still there. The electrons are still there. But the real story is happening in the invisible structure that connects everything together. And now we arrive at a conclusion that feels almost unsettling once you really let it sink in. If energy is not being carried through the wire by traveling electrons, and if what actually spreads through the system is an electromagnetic field, then most of what you think you are interacting with is not matter moving through space. It is fields interacting with fields. When you touch a wire, you are not feeling electrons rushing past your skin. When a device turns on, it is not because particles completed a journey from one place to another. What you are seeing is a local response to a field that has already reached that location. This idea shows up everywhere once you start looking for it. Every electrical system, every signal, every circuit is less about things moving long distances and more about patterns spreading through space. The motion of electrons is real, but it is small, local, and secondary. The dominant story is the field. And this should make you pause for a moment, because it means that the flow you imagined your entire life was never really there in the way you pictured it. There is no stream of tiny particles racing through wires delivering energy from point A to point B. There is a coordinated response happening across an entire system, driven by invisible structures that exist even in empty space. You are not watching matter travel. You are watching relationships update. You are watching the state of a field change, and every part of the system adjusting to that change almost instantly. In other words, electricity is not a story about objects moving. It is a story about connection. And once you start thinking this way, it becomes very hard to draw a clean line between what is in the wire and what is around it, between what is material and what is empty space, because the thing that actually carries energy does not belong neatly to either category. It exists in the structure that connects them. So let's go back to the statement you started with. Electric current is the flow of electrons. Now you can see why that sentence feels both true and completely misleading at the same time. Yes, charges move. Yes, electrons drift. That part is real. But that is not the mechanism that explains what you actually observe. It is not what makes your light turn on instantly. It is not what carries energy from the source to your device. The real story is deeper. What actually propagates through the circuit is an electromagnetic field. That field spreads at nearly the speed of light, reorganizing the entire system at once. The electrons respond locally, passing along energy through interactions, while the energy itself flows through the space around the wire, guided by the structure of the circuit. So when you say current flows, you are not describing particles racing through copper. You are describing a coordinated pattern of motion driven by fields, happening everywhere in the system at the same time. And this is the part that should stay with you most of the time. What you think you are seeing in physics is a story your intuition created to make things feel simple. Little objects moving from place to place causes traveling along clear paths. But reality is often stranger than that. Sometimes what really matters is not the objects, but the invisible relationships between them. Electricity is one of those cases. There is no river of electrons rushing through your walls, powering your life. There is a field filling the space around you, constantly shaping how charges move and how energy is delivered. And once you understand that, the next time you flip a switch, it stops being a simple action. It becomes a reminder that the world you experience is not built from the pictures in your head. It is built from rules that operate beneath them, rules that are quieter, less intuitive, and far more fascinating than the stories you were first.